Okay, let's do the exercises of section 11. Right. What are the maximal simply ordered sets of this relation? So this is the regular if p minus a is greater than 0, same thing. But and it has to be rational too. Yeah. So essentially all the maximal simply ordered sets would be some real number times rational numbers, and yeah. Essentially these are the maximal simply ordered sets. R is fixed, but the rational numbers are. And these would be maximal because if we take any other thing, then, well, either it is rational, in which case we have nothing to do, and if it's not, then it stops being rational and not comparable, and hence not maximal. So we can only add another real number, right? So since we're comparing real numbers. So yeah. Okay. So show that we can get partial order axioms and strict partial order axioms from each other. Okay. So what do we have? We have non-reflexivity and transitivity, right? For this bad notation, yeah, yeah. Now A is less than equal to B if and only if A is less than B or A is equal to B, right? Okay, yeah. So let's check for this one. So this means what? This means, well, A is equal to A by definition since they're the same symbol, and therefore this is true for all A belongs to A. So reflexivity is trivial. What's next? Yeah, antisymmetry. So well, A is less than B and B is less than equal to A. So that means, well, we have either A less than B or B less than A or A is equal to B, right? Now we can't use totality here. Keep that in mind. But we can use transitivity if since both of these are true. Then if this is not true, then both of these will be true, right. You can check the or cases. So what does that mean? That means by transitivity, A less than A, which is not true by non-reflexivity. So that's a contradiction, and therefore this must be the case. Which means, well, that's exactly what we have. So we're done. What's the third one? Transitivity, yeah. Okay. So A is less than equal to B, and B is less than equal to C. Yeah. So either A is less than B or A is equal to B. Either B is less than C or B is equal to C, right? Okay. Now, if so, we'll go case by case. If this is the case, then by transitivity of the simple order, A is less than C, right? If this is the case, uh, then since B is equal to C, A is less than C, so we're done. If these two are the case, then A is equal to C, which is also the case. So or, right? So it's fine. And lastly, if this is the case, then A is equal to B, so A is less than this case. So in every single case, we have this thing being satisfied, and that's precisely what it means for A to be less than equal. So yeah, we're done. Now we have to show that if we have a partial order, which is basically these three axioms, we can make a strict partial order from it. Okay. So, and it's defined as, so P is the partial order defined by those axioms. And okay, ASB if APB and A is not equal. Right, is that it? Yeah. Show that it's a strict partial order. So for non-reflexivity, what do we have? We have A, well, A is equal to A. So A can't satisfy A and A together can't satisfy A is equal to A and whatever nonsense. In this case, we'll have A is less than A, right? This, so yeah. it can't satisfy this because A is equal to A, right? Yeah. So because of that, A for all A not of A less than A. I'm just gonna write as one. Yeah, B. Okay. So it's not reflexive because A is always equal to A, and we need A to not be equal to A to allow for A as B. Yeah. Now for transitivity, let's assume A as B and B as C, and we have to show that A as C. So you have to show A is not equal to C and A is yeah, A is APC basically. Okay, so we have APB and A not equal to B. A in this case it's and here, mind you. BPC and B not equal to C. Okay, now if so, I think we're allowed to use the transitivity of equality since it's an equivalence relation, right? So how do we use that? Let's see. So A equal to B and B equals C implies A is equal to C. So the contrapositive would be A not equal to C implies A is not equal to B or B is not equal to C, right? Is that okay? No, that's not helpful at all, is it? Yeah, it's not. Oh well, I'll have to think about it. Let's see. So BPB and BPC implies A, APC, right? That part's completely fine. Hang on. Okay. So if A is equal to C, how do we use that? Oh yeah, it holds in multiple ways too. So A is not equal to C. Sorry, let A be equal to C towards the contradiction, and let so A is not equal to B. So and B is not equal to C, right? So C is not equal to B and not helpful. Hang on. Yeah, so I thought about it. Let's see. So if we have to show that A is not equal to C, right? So towards the contradiction that A equal to C, right? So if A and C are the same thing, then well, APB, hang on. So APB and BPA, that's true, right? And we don't care about these two actually. So with these two, what do we get? By anti-symmetry, we get A is equal to B, and that's a direct contradiction. So because of that, A is not equal to C. So that's what we're using the anti-symmetry thing for that. Yeah. Okay. And last, what's the last one? For that, that's it, right? Yeah, that's it. So we can get the strict order from the partial order and the partial order from the strict order. So yeah. Okay. Yes, this won't work. I'll just give a small example. Suppose we take a circle, right? So this is our x, and we have this. It's a part of the set because, well, it's contained in it. So I'm using the contained strict partial order, right? And this is also contained in this. But are these two comparable? Absolutely. Neither of them is a strict subset of the other. Or you can even want have them intersect, doesn't really matter. So yeah, that's a counterexample, and that's enough for the proofs. Okay, given 2 points, define this. Let's see. Yeah, so given that definition, essentially, yeah, so I'll just draw the curves and then we'll see the example. Why right? Yeah. Okay. Okay. So essentially if we can draw if it's going along some line of non-negative slope, then we get this being greater than that, right? So if it's going along a line of non-negative slope, then y bar is greater than x bar, and this is essentially a point. It's a vector, so that. Yeah. So y is equal to 2 is a simply ordered set because you add any other point to it. Well, this point and this point are not comparable, are they? Sorry, yeah. These 2 points aren't comparable, I think, because yeah, the same x coordinate are equal, and at the same time the y coordinates are unequal. So yeah, and you can generalize this for any point. It'll not be equal having the same y coordinate. Y is equal to 2, and there exists the next uh, there exists a point with the same x coordinate, and they can't be compared. So yeah, same thing with y is equal to x cube. So take any point, same y coordinate, same x coordinate, but different y coordinate, and can't be compared, right? For these two, this is not even a simply ordered set because here the y coordinate is the same, but the x coordinate is different. Hang on, that's not it. It was something else. Yeah, here the y coordinate is lesser, right? But the x coordinate is greater. So what does that mean? We don't even have the order defined if the y coordinate is lesser. So yeah, or at least the y coordinate is lesser and the x coordinate is bigger or something like that. So either the entire thing has to be no, or the entire thing has to be no. The entire thing also cannot be no. But yeah. So anyways, play around with it. The class of maximally simply ordered sets are the sets of increasing functions. Sorry, non-decreasing functions. So something like this also works. And yeah, I'm just leaving you to play around with it. And this is quite a simple problem actually. And I just realized I skipped question 3, so I mean I skipped the second part. So for the circles, this procedure I just showed how it won't work, right? Yeah. What about the other one? If the same y coordinate and that, okay. Uh-huh. So you take that and then okay, this procedure might just work here. So is that the case? Let's see. All the comparable ones are lying. So you pick a x coordinate, x point, right? And you add any point that's comparable to it, and they're all going to be horizontal lines. So yeah, the procedure would work there. So yeah, question 4 is done. Question 3 is done now. Okay, show that Zorn's lemma implies the following. So to recall, if any simply ordered set has an upper bound in the partially ordered set, strict partial order or non-strict partial order? Let's see. I think it wasn't strict. Oh, it is strict. Okay. Yeah. If there's an upper bound, then there exists a maximal element, which means there is a set that is it's never lesser than any element in the set. Okay. Yeah. So for it's simply ordered by proper inclusion and the union is belonging to it, then yeah, okay. So we take a collection of sets, and this is strictly partially ordered by proper inclusion, right? Yeah. Now we just need a set that is properly contained in no other set. So that's exactly what the maximal element is. And so let's say we have a chain, right? A chain or a simply ordered set. The subset of A. So let's say this is simply ordered. Now this has an upper bound. Why does it have an upper bound? Its union is, well, what? Its union would be, yes, it's sub-collection, sorry. Its sub-collection union would be, it's by hypothesis a member of this main collection. And you can see that since it's the union of all the members, it's going to contain every single member of it. So it's going to be, this is going to be strictly bigger than every B belonging to the collection, right? So in other words, this is an upper bound for every member of the simply ordered set. And since we have an upper bound by Zorn's lemma, we have a maximal element. And the maximal element by definition is a set A which is contained in no other. Something like that. Yeah. Yeah. So that proves question 5. Okay. Yeah, this is nice. If a collection of subsets of a set X is said to be of finite type, provided the subsets. Okay, yeah. So B, how is it written? Collection of subsets of a set X. Okay. So A is a subset of power set of X, right? And B belongs to A. Is it B? Yeah. B belongs to A if and only if for all C which is finite and C is a subset of B, C is in A, right? So all finite subsets of B belong in A. So yeah, so that's what it means to be a finite type, and we have to show that even such a set would have no such a collection would have a set that is not properly contained in any other set. Okay, so we just have to show that union is there, right? So how do we show that? So let beta, I'm going to call it beta, be a subcollection of alpha, right? Yeah. Now we have to show that union of beta is a member of alpha, essentially, right? Okay. Hmm. How do we do this? Let's see. Yeah, so I thought about it, and so how do we show that the union is in A, right? So take any, so for this set, I'm going to call it B prime. Take any C that's finite, any arbitrary C, and this C is a subset of B prime, right? So since it's finite, it's going to have a fixed cardinality. So let's call it N, right? Sorry, it's going to have a finite cardinality, and from that we can order them from 1 to N, right? Okay. Now for each of these, there's going to be a so since C1 is a finite set and it's coming from so every member C1 has to come from some element of this collection B, right? So I'm going to call that member P1, right? So each of them have to come from some Bn, right? So Cn belongs to Bn and Bn belongs to collection B, right? And I'm exploiting the finite type property here. So singleton C1 is a finite set, and there's going to be at least one a member of the collection that's going to contain C1 in it. So yeah, we have a bunch of finite sets. Now note that is it simply ordered? No, it's not simply ordered. What is it? What's given to us? Yeah. Okay, so finite type. Now, yeah. Now we just have to show that C is contained in some BK, right? So how do you show that? By induction. So assume that if C is of cardinality less than n, so for a singleton we have B1, right? That's trivial. Now if C has cardinality n and C does belong to some BK, now if C has some cardinality n plus 1, right? That we have two cases now essentially. If yeah, we have the choice BK here or Bn plus 1. And the point is one of them must be contained in the other. Is that true? Why should one of them be contained in the other? That's because I think, yeah, it's corresponding to the finite type thing again. That's because if, hmm, yeah, I forgot that we were assuming that it's a sub collection that's simply ordered by inclusion. So because we're assuming the Kuratowski lemma here or the Tukey lemma. So yeah, this is actually simply ordered by inclusion, and therefore we have either Bk or Bn, like Bn plus 1, and one of them must be greater than the other. And because Bk contains the entirety of the set Cn C minus Cn plus 1, right? And Bn completely contains this and Pk, so C must be contained in the new choice, essentially. So yeah, for every finite cardinality, we can find one among these such that C would be completely contained in it. So what does that mean? That means, well, since any arbitrary finite subset is belonging to alpha, since Bk being there implies C is in there, well, this thing must also belong to alpha. And yeah, this is a separate thing, right? Yeah. So yeah, that's the proof. You essentially prove it by induction on the cardinality of this finite set. And then you choose the biggest member, and since the biggest member is here, then C must be in here, and then you can go back to B prime. So yeah, that's how you show the Tukey lemma. And now let's show the Hausdorff maximum from this. Okay. Yeah, so let this be a selection of partial ordered sets, like a collection of sets with a strict partial order on them, and let beta, I'm not sure. Yeah, I'm going to call this set something else. Be the set of subcollections which are strictly simply ordered, right? So all the subcollections that are simply ordered. So now if I show that they're of finite type, we will have a maximal element, right? Yeah, we'll have, yeah. If we show this set, which is, actually, yeah, forget it. So the partial order is something, no notation is given to it, just assume it exists. And this, we have to show is a finite type. If we show this is a finite type, then we're done with the problem, essentially, because the set has to be maximal because it is contained by no other simply ordered set. So yeah. Okay. Now, how do we show it's a finite type? That's actually pretty easy. Yeah. So for all, mm, yeah. So if B is an A, I'm going to call them B. If B is an A, then you take any finite restriction of it, it's going to be simply ordered as well because any restriction is simply ordered. So every finite subset is there. So one direction is trivial. Now, if any arbitrary finite set of subset of B is simply ordered, can we show that B is also simply ordered? That's the question. So to show that B is simply ordered, we need to show for all A comma B comma C, A less than B, B less than C implies what A less than C. So keep in mind the set A comma B comma C is a finite set of three members, and since they are simply ordered by assumption, transitivity holds, including totality. And what's left? Non-reflexivity. Non-reflexivity. That also follows from any finite set that's containing the singleton that you want to exploit. So yeah, because of that, you can choose your favorite triplet that will be simply ordered by assumption, and because of that, the whole set will be simply ordered. So yeah, this shows that calligraphic A is of finite type, and that shows the Hausdorff maximum principle. Maximum principle. Okay, yeah. So first, I'm assuming you've read the question. Yeah. So I'm going to show it through contrapositive since independent is the same as not dependent or not having a sum that equals zero that does not have all members zero. So the statement is equivalent to showing that if A union B is dependent or has a sum AI xi plus B equals zero, which is dependent, then A is dependent, right? Yeah, essentially. But keep in mind that V is outside the span of A. So this gives us a contradiction since, yeah, okay, so V is outside the span of A. So V is definitely not equal to AIXI for any combination, right? That's what it means to be in the span. So what does that mean? That means B has to be zero, and that means A is dependent. So that's one way of looking at it. Or if you assume that A is independent, then this can never be equal to zero, and that means B is in the span. Either way, one of the assumptions are violated and is violated, and yeah. So this shows that if A is independent and B is outside the span of A, then this is independent. Okay. Show that the collection of all independent sets in V has a maximal element, and that's because you take their union, it's also going to be an independent set. And why is that? Let's see. So we have a collection V of independent sets, right? Yeah. So their union is going to be independent because, well, we take any finite linear combination. Uh, yeah. If we take any finite linear combination, well, they're all going to belong to something. Hmm. I think we should use Zon's lemma, but let's see how. Yeah, I hope you can hear me. Yeah, I thought a bit harder about it and observed that this this set is of finite type. So this set is of finite type because we're taking a finite sum and we're checking whether it's equal to zero or not, right? And if it's never equal to zero, then we're done. So if we take any finite subcollection, then well, yeah, you take any finite collection, that's also going to be linearly, it's also going to be independent because the whole set is independent. So if that ends up being dependent, then the whole set isn't independent, which means it's dependent. So because of that, this is a finite type, and that directly shows that it has a maximal element at the very least if we compare it with respect to proper inclusion. So yeah. And V has a basis because well, its maximal element is precisely the basis because if you add any more elements to it, then it contradicts the maximality. So yeah, it's the element that's not contained in any other. So it cannot be contained in any other independent set. And yeah, if so, essentially, if A is independent and if V does not belong to the span of A, does belong to the no does not belong to the span of A, then A union V is independent, and that's a problem because it contradicts the maximality of it. And that's why the maximal element of this set, which I'm going to call A, is precisely the basis of B. So yeah.